We are now going to learn how to use an Excel spreadsheet in order to be able to draw a scatter diagram for our variables, for our information, get the least square regression line, and information we need to determine whether or not there is a relationship between the explanatory variable and the response variable. In this particular problem, we have the heights and weights of 11 men between the ages of 21 and 26 that were measured. The explanatory variable is the height, so we have all the heights listed in this row, and their weights would be the response variable. And we're going to want to be able to determine whether or not there is a linear relationship between the height and the weight of the men. So looking at our data, we want to draw a scatter diagram. So we're going to go to click on these two rows. We go to Insert, we're going to the Scatter Plot. We only want the points, and here we have the scatter diagram of this particular information. And just looking at the plot, we notice that there appears to be a linear relationship between the height of the men between 21 and 26 and their particular weights. Well, in order to go any further on this, we want to compute the linear correlation coefficient between the height and the weight of the men in the sample. And that is our Pearson correlation coefficient, denoted by the letter R. In order to do that, we're going to go to our formulas. We go to statistical, and we're going to the word Pearson. And that is, if you look at that, returns the Pearson product moment correlation coefficient R. It doesn't make a difference whether we put the X and the Y's here, because if you looked at the PowerPoint, you saw the formula for that. So the first array, I'm going to put in the heights of the men. In the second array, I'm going to put in the weights in pounds. And you have the correlation coefficient right over here. And we look at that, and we have 914 thousandths, which tells us that there is a fairly strong linear relationship between the height of the men and their particular weight. And that's the comment on the type of relationship that appears. Now we want to be able to use this information to predict other pieces of information. In order to predict other information, in other words, using this particular sample, we have to be able to write a least square regression line, which is in the form of y equals mx plus b, m being the slope, the b is the y-intercept, and we can only use it for a group of men between the ages of 21 and 26, whose heights range from 66 inches all the way up to 76 inches. So we have that particular spread. In order to do that, we have to find both the slope and the y-intercept. So to find the slope, again, we go to our formulas, we go to statistical, we look for the word slope, and when we find that, you notice that the slope, it tells us, returns the slope of the line, and because we're looking for slope, the slope of the linear regression line, we have to take the y array first, which means we're looking at the response variables, which are the weights, divided by the x's, which is the explanatory variable or the heights, and we notice that that is 5 371 thousandths. For the y-intercept, basically, again, we go to statistical and we go to the word intercept, and it tells us, it calculates the point at which the line will intersect the y-axis using the best fit regression line plotted through the known x and y values. In other words, what will the y value be when x is equal to 0? Again, we're going to put down the y values, which are the weights, followed by the x values, which is the height of the men. And we notice we get a negative number, which means that if the men are 0 inches tall, they're not going to weigh anything, which doesn't really mean anything. But we write the least square regression line, which means we're going to take our y hat, because that's how the regression line starts, is equal to the slope, which is 5 371 thousandths, times x plus the y-intercept, which is a negative 203 and 58 thousandths. And that gives us our particular regression line. Now, what we want to do is use the regression line to predict the weight of a man who is 73 inches tall. Again, it's within the range of heights that we have, so we can use the least-square regression line. And using our information, our regression line formula, we have that the predicted y, or basically the y hat, is going to be equal to the slope times the height of the man, which is 73 inches, plus the y-intercept. And that tells us that that man is approximately, let me put the hat down over here, is approximately 188 and 5/10 of a pound. Well, that gives us that information, but we want to calculate the r squared, which is the coefficient of determination. The coefficient of determination tells us what percent of the time the response variable is influenced by the predictor variable or the explanatory variable. In order to be able to calculate the coefficient of determination, we take the r, the correlation coefficient, and we square it. So we put down equals the correlation coefficient. We're going to square that particular value, and that gives us 836 thousandths. Now, in order to interpret the coefficient of determination, we take this and change it to a percent. So we have 83.6 and 0.6% of the variation in the weights is explained by the least square regression line. In other words, about 83 and 0.6% of the time, we can say that the weight of the man is determined or can be predicted based upon their height. There are lurking variables that also might influence these men's weights, and we don't know what they are, but we can use any information such as their eating habits or maybe the amount of time that they exercise. But that basically gives us some information about the influence of the explanatory variable on the response variable.